Okay, we can also use Cauchy in combination with the residue theorem to sum series in a fairly general way. Okay, let's let Cn be the square with side length 2n plus 1 with sides along the real part of z equals plus or minus n plus a half, and the imaginary part of z equals plus or minus n plus a half. All right, so it's just going to be a square like this. Taken in the positive orientation. All right. If f of z is a meromorphic. Now, this is a word that I don't think we've used yet. Meromorphic means analytic with the exception of a number of isolated poles. Okay, a meromorphic function is a function that is entire except it's allowed to have poles. Any number of them. It can even have infinitely many poles, but it cannot have essential singularities. It cannot have branch cuts. All right. It's analytic with the exception of a number of isolated poles. They can be poles of any order, but they have to be poles. They can't be essential singularities or not isolated. Okay? There's a wonderful theorem by virtue of Weierstrass, which indicates that all meromorphic functions can be understood as a ratio of two entire functions. All right? So it's like meromorphic is like a rational number. All right? Whereas an entire function would be like an integer. Okay? A rational number is a ratio of two integers. A meromorphic function is a ratio of two entire functions. Yes, sir.
Does it exclude like the non-isolated singularities when they get when poles get consistent with those?
They're not allowed to do that inside the finite plane. Now, I said there could be an infinite number of poles. How could there be an infinite number of poles if they don't bunch up? Well, the only way that they can do that is if they go out to infinity. If they bunch up around infinity. Infinity is not in the finite plane. So infinity is not included. Does that make sense? So for example, the cosecant function is meromorphic. Even though it has an infinite number of poles at pi times all integers, but they're all poles. They don't bunch up. Okay, and it certainly is a ratio of two entire functions. The cosecant function is 1 divided by the sine function. 1 is entire, the sine function is entire, so it's a ratio of two entire functions. All right? So, if f of z is a meromorphic function throughout the plane with no poles on Cn, and this limit is equal to 0, okay, then we can show, and this takes a minute to show, but it's actually pretty straightforward once you get into it. Oh, sorry, limit as n approaches infinity. All right, as n approaches infinity, the integral of f of z pi cotangent pi z dz is equal to 0. Okay? Now, why is that relevant? Well, what's interesting here is that the cotangent function comes with its own poles. The cotangent function is cosine divided by sine. So the cotangent function has poles at all integer values of z. Okay? That's because it's cosine divided by sine, and the sine of pi k is equal to 0 when k is an integer. Okay? The fact that this integral is equal to 0, which, by the way, we're not going to show it, but you show it by integral bounds. All right, and as I said, it just takes a little bit of time. All right? But it's essentially because of this limit. The cotangent function effectively approaches a constant as z approaches infinity, because cosine and sine approach the same magnitude as z approaches infinity. We make sure that we're doing n plus a half, so we don't go through any of the poles of the cotangent function. And of course, is an integer. I don't think I said that. All right. And the fact that the limit of z, f of z equals 0 is going to clinch the fact that this integral goes to 0. The reason I have to multiply by z is because that's effectively the length of the contour. Remember, integral bounds says that the modulus of the integral is less than the maximum modulus of the integrand times the length of the contour. All right, so I have to multiply by that length. So it's not good enough if f of z just goes to 0 by itself. I need z times f of z to go to 0. But once we have that, this is equal to 0. And now we can do this integral by residue. Okay? So I could say that this 0 is equal to 2 pi I times the sum of the residues of the integrand. So I'm going to have the sum of the residues of f of z pi cotangent pi z at all integers plus the sum over all of the poles of f of z, which I'm going to call zk. And I have to abbreviate this because I've run out of chalkboard. But the residue at those poles. All right. They come from F. F we said was a meromorphic function. So F is allowed to have its own pole structure. Okay? Yep.
Do we need to be careful that I guess the poles don't collect? If F of Z is one of the same poles that the cotan does, is that an issue?
Then they're only included once in this one.
Okay.
Okay? All right. Now, what are the residues of F of Z pi cotangent pi Z at the poles of pi cotangent pi Z? Well, all the poles, as long as one of you just pointed out, as long as they're separate, as long as you don't have a problem in F of Z, for example, at Z equals 0, as long as we have a simple pole in pi cotangent pi Z times F of Z, what is the residue? Well, it's going to be the limit as Z approaches K of Z minus K, F of Z pi cosine pi Z divided by sine pi Z. All right? And as long as F is analytic at K, we can now do this limit by using L'Hopital. I'll take the derivative of the numerator where it won't contribute unless I take the derivative there. Okay? And I'll take the derivative of the denominator. And this will give me F of K. All right? Because when I take the derivative of the denominator here, I get a pi that comes out. That pi cancels that pi. I get cosine pi Z, which promptly cancels the cosine pi Z, almost as if it had been engineered that way. All right? I wonder why. Anyway, so since this is 0, it tells us the following very, very, very useful formula. The sum from K equals negative infinity to infinity of F of K, where I have a prime here. That prime means I am omitting any integers at which F is not analytic. They're going to go on the other side. Because the sum of these two residues is 0, this one has to equal negative that one. So this is minus the sum over all the poles zk in F of Z of the residue of F of Z pi cotangent pi Z at zk. All right. Now we can use this formula to compute the values of the Riemann zeta function at even integers, even positive integers, if we like. All right, the reason is that when we do this sum, let's say that F of Z was 1 over Z squared, for example. Well, 1 over Z squared is not analytic at Z equals 0. Okay? But it is analytic in all the other integers. So we would get the sum K equals minus infinity to infinity prime, where the prime means omit K equals 0. 1 over K squared is equal to minus the residue of 1 over Z squared pi cotangent pi Z at 0. Okay? And we can find that residue fairly easily. Let's see how it goes. I'm going to do it by series because I don't want to have to take the derivatives. This has a pole 3, and I just don't feel like it. All right, so I'm going to do it like this instead. Pi over z squared. It's going to be cosine pi z divided by sine pi z. So this will be pi divided by pi z cubed. I took out a pi z out of this expansion. I'm going to have 1 minus pi squared z squared over 2 factorial plus, I don't care because I only want z squared. I'm only interested in the coefficient of 1 over z. Is everybody with me on that? Because that's what the residue is. The coefficient of 1 over z. Divided by, in this expansion, I factored out a pi z. So it'll be 1 minus pi squared z squared over 6. Plus dot, 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 dot. The pi's cancel out. 1 over z cubic. And I'll have 1 minus pi squared z squared over 2 geometric. 1 plus pi squared z squared over 6. And when I multiply that out, I find that the residue is minus pi squared over 2 plus pi squared over 6. Which is minus pi squared over 3. Minus negative pi squared over 3. And that's equal to the sum prime from negative infinity to infinity. Since we're doing k squared, and the square of a negative number is the same as the square of that positive number, this is equal to 2 times the sum from k equals 1 to infinity of 1 over k squared. Dividing by 2 gives us pi squared over 6, the well-known result from Euler. Okay? Now, that's sort of a neat example. It's a well-known example, which is why I did it as the first one. But there are easier ways to get that result. This is not the cleanest way to get that result. And it would be awkward to get that result for a higher power. However, it does make it clear why we can't get the sum of the reciprocals of the third powers. Because what will happen if this is k cubed is that the negatives and the positives will cancel each other out. So I can't use this approach to get the odds. I can, however, use it to get all of the evens. All right? What is perhaps a more esoteric result is this sum. The sum from k equals negative infinity to infinity of 1 over k squared plus 1. Okay? This function has poles at plus or minus I, and they're both simple poles. So this is going to be minus. Neither of those poles are integers, so I don't need a prime or anything. We all good. So I'll say minus the residue 1 over z squared plus 1 pi cotangent pi z at I minus the residue 1 over z squared plus 1 pi cotangent pi z at negative I. All right. To do the residues, I'll use L'Hopital. All right, so this is going to be minus pi cotangent pi I divided by 2I minus pi cotangent minus pi I divided by negative 2I. Okay? So let's massage this into a better form because that's a little bit messy looking. All right? Get rid of all this. And we'll have the sum from negative infinity to infinity, 1 over k squared plus 1 equals minus pi over 2I. And then it's going to be the cosine of I pi divided by the sine of I pi. And then it's going to be plus pi over 2I. Cosine of negative I pi is just the cosine of I pi divided by the sine of negative I pi, which is going to be negative the sine of I pi. So these two are going to give the same result. What is the cosine of I pi? That's e to the I pi plus e to the minus I pi divided by 2. That's equal to e to the pi plus e to the minus pi over 2, or cosh pi. Okay? The sine of I pi is e to the I pi minus e to the minus I pi divided by 2I. That's equal to e to the minus pi minus e to the pi over 2I, or I sinh pi. Okay? So pulling this all together and remembering that these two are the same, so I'll just get rid of the 2 and only write one of them, I would get I pi cosh pi divided by I sinh pi. Right? So that gives us the famous result for this series. The sum from negative infinity to infinity, 1 over k squared plus 1 is equal to pi cosh pi, which is sort of interesting. And it really is equal to this. Pi times e to the pi plus e to the minus pi divided by e to the pi minus e to the minus pi. Seems kind of strange that a simple series like this one, think about what this is. K equals 0, 2 times all the other integers because I get positive and negative. When k equals 1, when k equals 2, when k equals 3, when k equals 4, when k equals 5, when k equals 6, and so on and so forth. It's kind of strange that that would be equal to pi times e to the pi plus e to the minus pi divided by e to the pi minus e to the minus pi. But it is equal to that. This is kind of a neat way to sum series. Note that we can do the same thing for series involving a negative 1 to the k. All we do is we modify our treatment a little bit. And what we'll end up with is the following formula. Sum again prime negative 1 to the k f of k and it's going to be minus the sum over the poles of f of z But instead of doing the residues, oops, I should have said residue, my gosh. Residue of F pi cosecant pi Z ZK. Remember before we had the cotangent, it was cosine divided by sine. And when we did L'Hopital's rule, the cosine canceled out. Here, I just have 1 divided by sine. So when I do L'Hopital, I'll get the cosine still there and it won't cancel. The cosine of pi k is minus 1 to the k. So that's why that comes out. So this allows us to also compute the value of alternating series. Okay?